Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial video, I'll continue these topic 4 topical MCQs on states of matter, as well as the gas laws that involve the Boyle's law, Charles' law, Avogadro's law, the ideal gas law, and so on and so forth. Yeah? So in this first question, so looks like this is ideal gas question. So we've been given the temperature in 60 degrees Celsius. So in the ideal gas equation, you have to convert temperature in degrees Celsius to Kelvin. So I just have to add 273 and I get 333 Kelvin. It's important that you write unit very clearly. The unit of pressure given was in kilopascal. To put it into ideal gas equation, you need to convert it into Pascal, where 1 Pascal equal to 1 Newton per meter square. So that's why we need to convert it to Pascal. Okay, and the volume has been given in meter cube, so that is all good because meter cube is the SI unit of the volume in the ideal gas equation. So you want the mass of the sample of ammonia, so the mass will be something gram, and we need the molecular mass of NH3 gas, which from your periodic table is just 14.0 plus 3 times 1.0 will give you 17.0. And of course the calculator will show you 17, but you know, these are just usual things that you can get the accuracy from reading the periodic table itself. Yeah? So PV equal to nRT, so that's mass over MR, give you the N, which is the mole of the gas. And I want the mass of the gas, so it's PVMR over RT. R is given in the data booklet as 8.31 joule per mole per Kelvin. So that's just the molar gas constant. Now that I've got everything with the units laid out properly, so what I can do now is I can just sub everything to the equation. So 103, 000. So there's no point of me writing them in anymore. But once I've got everything sorted out, once I rearrange the formula, then I can be nice and happy to put everything to my calculator. So 103,000 Pascal times 5.37 times 10 to the minus 3 times 17.0 divided by 8.31 divided by 333, and what I obtain is 3.3979 gram, and they want it to only 2 significant figures, so there's 3.4 gram. I bet one of the answers here would be where the temperature is just 60, and that's usually there because some students will have forgotten to convert degrees Celsius to Kelvin, and that's one of the key mistake that you can do when tackling this kind of ideal gas equations. Yeah. Question 32. Under which set of condition is a gas most likely to be ideal? So you want it to be ideal gas. So one of the most important assumption of an ideal gas is negligible intermolecular forces, which I will abbreviate from now on words as just IMF. So you want to have negligible intermolecular forces, so you want the intermolecular forces between the molecules to be as small as possible. When the molecules are close together under high pressure, obviously you have stronger attraction between the molecules because they are closer together, and that is possible when you're under high pressure. So you don't want high pressure, you want low pressure where the molecules are much further apart, where there will be negligible intermolecular forces, or at least very minimal forces of attraction between the molecules since they are so far apart. And you also want that to happen at high temperature, because at low temperatures the molecules would have the gaseous molecules of the gaseous particles would have very little amount of energy, and with little amount of kinetic energy, they won't move as far apart from each other, therefore they'll be closer together, and therefore giving you non-negligible intermolecular forces. So only at high temperature they have enough kinetic energy to move further apart, and therefore results in these negligible intermolecular forces. So high temperature, low pressure, something you'll be expected to explain and describe in detail in a paper 2 or paper 4 kind of setting. Yeah. Next question, question 33 is basically Boyle's law, something you have done from O-level or IGCSE or GCSE physics. Volume against pressure. So PV equal to constant, that is Boyle's law, but it's incomplete unless you specify it is at constant temperature, which is what they have done. All right, so PV equal to constant, that means P is inversely proportional to V. Okay, because you can move out the V, then PV equal to constant, or P equal to constant over V, then PV equal to constant. This is the relationship inverse proportion. These are direct proportion. This means there's no effect. As pressure increase, volume does not change. This means volume is not, it has no relationship with pressure. The only inverse relationship that we have from these options would be D, where pressure, whether they are on the X or on the Y, this is an inverse proportion kind of graph. Yeah, so very direct and straightforward then. Question 34, we are back to more ideal gas kind of question. It is ammonia again, just like the previous question. The temperature is different, but you have to convert it to Kelvin. The pressure is in kilopascal, you have to convert it to Pascal. The volume is in meter cube, which is not a problem anymore. So the temperature converted to Kelvin, just add 273, and I get 313 Kelvin. The pressure converted to Pascal, I just multiply by 1000 and I get Pascal. So it's important that we write the unit on the value that we put down, because you know it's very easy to get confused. Okay, so the MR ammonia. So ammonia is just NH3, something you will have been expected to know since your O-level days or GCSE or IGCSE days. So 14.0 plus 3 times 1.0. Your molar gas constant come from your data booklet, so this is joule per mole per Kelvin. Set up your ideal gas equation. PV equal to nRT. N is the number of mole of gas, is equal to the mass of gas divided by the MR of gas, time RT. You want the mass, so it's PV MR over RT. I wouldn't substitute, I wouldn't write down where I substitute all of these into the expression. Once I get the expression, I would just put in the value, but only because I have everything sorted out nicely and written out nicely like this. Alright, so 95,000 Pascal times 4.32 times 10 to the power minus 5 times 17.0 divided by 8.31 divided by 313, and my calculator show me 0.02682. They don't tell me how many significant figure, but looking at the value given, they are all to 2 significant figure. So if I just and they are all in standard form as well, so if I convert this into standard form, so move 2 places there, just like a primary school maths, that will be 2.7 times 10 to the minus 2 gram. I move the decimal place 1, this time 10 to the minus 1 times 10 to the minus 2, I'll get 2.682 times 10 to the minus 2, and then you can round it up to 2 significant figure. Since this is greater than 5, I add 1 there, I get 2.7 times 10 to the minus 2 gram. This is the last question of this 5-question series. So previously we had a question for conditions that will give us the gas which behave most ideally, whereas here you want the gas that behave least like an ideal gas. All right, so instead of conditions here is the molecules that are different here. So again, most ideal is most ideal gas have negligible, actually has negligible intermolecular forces. So least ideal would mean the least negligible. Okay, therefore least ideal mean the least negligible. IMF meaning strongest intermolecular forces. All right, strongest intermolecular forces. If you look at CO2, helium, hydrogen, and nitrogen. Okay, if we look at van der Waals, so obviously all of them have van der Waals, right? And van der Waals depend on the number of electrons. And of course, looking at helium and hydrogen is only 2 and 2 electrons. This one has got 7 protons times 2, 14 protons. So it's got 14 electrons. So it's got 6 proton plus 8 times 2, which is 16 plus 6 is 22. So there's 22 electrons because number of electrons in the molecule equal to the total number of protons, since there are no overall charge in any of these. All right. Looking at this, I can tell you that helium and hydrogens would have the weakest van der Waals. So this one would have the weakest van der Waals. Therefore, we are not looking at helium and hydrogen to get the strongest intermolecular forces. We have to consider, in fact, when you consider permanent dipole, this is non-polar as well, because these are of the same atom, so they have the same electronegativity. That's why the molecule is non-polar. CO2, carbon and oxygen actually have different dipole moment, actually have different electronegativity. That's why there's a dipole there. But there's an equal and opposite dipole on the other side, because this is CO and this is also CO. So in this symmetrical distribution of charge, either side of the carbon, so resulting in the molecule being non-polar. Okay, so when you explain why CO2 have a higher boiling point than N2, it's not a result of a permanent dipole, but it's a result of the difference in the number of electrons, resulting in this having slightly stronger van der Waals than this. But the moment you talk about it having permanent dipole, means that it is polar, means that you have got the wrong chemistry concept. Okay, so carbon dioxide would be the least ideal. It's a result of the strongest van der Waals. Out of the 4, it's got stronger van der Waals than N2 as well, because it's got the greater total number of electrons, 22 electrons versus 14 electrons. Make sure that when you count electrons, you're not counting molecular masses. The electrons come from the number of protons, which must balance the number of electrons, since the molecule is neutral. There's no charge to it. All right. So this is the end of this 5-question series on states of matter and the gas laws topic number 4 in my classification. And don't forget to click the subscribe button at the bottom right of this video. And yeah, share the channel with friends, chat group, social network, juniors, seniors, whomever you think the channel might be useful for. Browse around the channel and look through the created playlist to see if anything else is of interest to you or someone you know. And thank you for watching, and I'll see you in the next video.